Now, to one of the approaches that which the closures are introduced in this is by the introduction of the concept of eddy viscosity. Now, I am doing all these things because of course, if you want to do turbulent combustion, suppose you want to solve a turbulent combustion inside an engine, you have to solve the flow also. Unlike in the laminar flames where we were discussing, like we were approximating the entire flow by that pressure gradient is small, and by the continued the rho u is equal to rho u. So, rho 1 u1 is equal to rho 2 u2, and here of course, you have to consider the detailed flow, and to model the detailed flow, this Reynolds average Navier-Stokes equation or this Fabre average Navier-Stokes equation is one of the possibilities. And of course, we will introduce the combustion models, but at least to for the first thing that you need, you have to solve the average continuity equation and the averaged momentum equation. So, that is why we are doing all these things. So, this is here essentially solution of the momentum equation or the average momentum equation. You cannot simplify it, and you have to solve it along with the your combustion equations. So, that is one important thing in turbulence that you should keep in mind. So, here we introduce this k-epsilon model. Where we introduce the concept of introducing the concept of eddy viscosity this Reynolds stress terms, which was the inside of was this. So, this Reynolds stress terms were this. And of course, we had a gradient in front like that. Now, if we call this as Reynolds stress, then we model that by the following. Nu T. This is just a model under the so, here the strain rate tensor is essentially Fabre averaged. This I is an unit tensor. Okay. So, this is how you introduce this thing minus there is a 2/3, okay, whereas K is the turbulent kinetic energy Fabre averaged. So, this term is essentially equal to, you can write it as Vi Vj double prime this thing. Okay. So, here it is written in this simplified form, but actually it includes both the cross terms also. So, essentially this is a tensor, this left hand side, whereas K is actually a scalar because of this thing, because K is defined as, that is the Fabre average turbulent kinetic energy is defined as this way. Fabre average turbulent kinetic energy is defined as K tilde is equal to half Vi double prime to tilde. Okay. So, this is a scalar defined at a point, whereas this is a tensor. Okay. Of course, scalar is also a 0th order tensor. So, anyways, but this is a full it is a second order tensor with the 9 elements inside it, this Reynolds stress. Now, this we can define this nu T, which is essentially a kinematic eddy viscosity. So, you see what we have done here, we have taken this Reynolds stress term and say that it is essentially diagonally proportional to the Fabre average strain rate tensor, and this proportionality constant is essentially this thing called the nu T is essentially, which is the eddy viscosity. Okay. So, this is the important concept of eddy viscosity, and that is needed because you found that when we do the when we introduce the Favre averaging in the Navier-Stokes equation, we are basically left with this term which does not have any closure. So, of course, this appears elsewhere. So, you and in this thing itself also. So, as you see here. So, essentially you will have strain rate inside this. So, and if this term is essentially proportional to the this what is inside is essentially proportional to the nu t times the strain rate tensor, then this can be coupled with this term which contains the normal viscosity, and then we can add the effective we can add the normal kinematic viscosity and this eddy viscosity together to basically form a effective viscosity. But typically in turbulent flows, I mean the effect of viscosity, normal viscosity in this will be much smaller than the turbulent viscosity, turbulent eddy viscosity. So, this is how the modeling is introduced. This is the first modeling that we introduce here, that is in the k-epsilon model, and we have not gone into the k-epsilon model yet. We will come to that because this is still we will see how to basically do this, because you see that we have still this term, that is a k equation which we need to basically have a model, have an equation for. So, to close this, this is the bottom line is that this is still not closed because you have got k. So, we need an equation for the governing equation for k tilde, that is the Favre averaged turbulent kinetic energy. Okay, and this will be given by the following. Now, before that we can write down nu t as essentially C mu times k tilde square by mean epsilon, whereas C mu the value is taken typically to be about 0.09. Okay. So, that is the thing. Now, so of course, you see that we have got then two terms in nu t itself if you put here, and this goes into this whole thing goes into the this average Navier-Stokes equation. So, essentially you get two more terms, that is k and epsilon. So, we need closure for those, and those closures are essentially provided by the k epsilon model, because you have k and epsilon here. So, that we have a governing equation of turbulent kinetic energy which can be exactly derived just like the way we derived it in the previous class, where for of course for that was for constant density flows. So, this is little more complicated, but the basic essence is similar. On the left hand side we have the transport of k, is equal to mean density Reynolds average sigma k, it is essentially a model constant, times nu t grad k tilde minus v prime double dashed Reynolds stress terms contracted with divergence gradient of v tilde minus mean of density times dissipation. Okay. So, essentially this is the which what we have is essentially the production term, and this is the dissipation term in the turbulent kinetic energy. So, and of course, as you remember in the production term you had this was preceded with the Reynolds stress terms, and then you have the velocity gradient, we have the velocity gradients. So, you get similar things here, all right, here also. Okay. So, that is the point, that is this equation, that is the kinetic energy equation, the kinetic energy transport equation, which you essentially need to have a closure for the previous Reynolds stress terms, the eddy viscosity closure. So, which you need for this itself. So, for that it can be essentially an exact equation with some model constants because of the introduction of these things. Okay. But the next equation is that is this epsilon equation of our turbulent or TK dissipation, turbulent mean turbulent kinetic energy dissipation rate. This equation, this is essentially an ad hoc equation, and there is no direct reason, direct ab initio, you cannot derive this ab initio, and rather this comes from the fact that this dissipation should also look similar to the previous equation. So, that is this term. Is equal to divergence of mean density nu t. So, this is once again this is an ad hoc equation which is required for closure, and but this works well in certain flows like turbulent shear flows, even density varying to some extent. Of course, as you see that because the modeling thing, it has a lot of ad hoc constants. And here you have sigma k is equal to 1.0. These are the different model constants that are typically used in commercial softwares. Okay. So, to summarize, as you see that when you of course, when you have basically here we are trying to deal with the flow. So, to deal with the flow you need to at least you need to solve two equations, that is you need to solve the continuity equation and you need to solve the momentum equation. So, in non-reacting flows, of course, in constant density flows in CFD you directly do not solve the continuity equation. It is comes from the pressure potential equation from the momentum equation itself, and then you implement the divergence of V equal to 0 criteria. But in density varying flows typically you solve the continuity as well as the momentum equations, and then in an average form, and of course, in an average form continuity equation does not have any problem, as you saw, that is it can be, this is the form of the average continuity equation with Favre variables, Favre average variables, and then when you introduce then when you do the same thing for the momentum equation, you see that of course this Reynolds stress terms emerging from the the nonlinear the convective acceleration term, and then you have this emergence of this Reynolds stress terms which are not closed. So, to close them we introduce this model which is essentially says that this Reynolds stress terms is essentially proportional to the strain rate. The Favre average Reynolds stress terms is essentially proportional to the strain rate tensor, and that is the Favre average Reynolds stress tensor is essentially proportional to the Favre average Reynolds Favre average strain rate tensor, and then that proportionality constant is given by something called the eddy viscosity. Okay. Now, eddy viscosity introduced has of course this k square tilde divided by epsilon, which can be defined in this form, and then of course you need to solve for this k and epsilon are unclosed, and that leads to the introduction of this turbulent kinetic energy or this k-epsilon model, where we have two equations for the turbulent kinetic energy, and where we have one equation for the evolution of turbulent kinetic energy and one equation for the evolution of the turbulent kinetic energy dissipation rate. Of course, for the turbulent kinetic energy evolution equation, that can be derived in a very systematic manner as we have did previously, which leads to the which shows us the production and the dissipation terms. But then there is no such governing equations for turbulent kinetic energy dissipation rate, at least in the scope of the k-epsilon model, and then that leads to the introduction of this epsilon model in an ad hoc manner, and which leads to several model constants. But at least with this framework, I mean it works well for essentially for like a turbulent jet or other shear flows. It does not work too well for density varying turbulent jets, but especially there are other problems with non-reacting flows, but at least this gives us an idea about how we can approach turbulent combustion modeling. So, at least the flow part can be settled to some extent with this Reynolds models. Of course, there can be more elaborate models like large eddy simulation, etc., but that we will not go right now. So, up to this point we have had a very solid we have shown you that to model the flow, at least you have the continuity and the and the average momentum equation, and for the to close the average momentum equation you need the this eddy viscosity closure, and for the eddy viscosity closure you need the Favre averaged turbulent kinetic energy equation and the dissipation equation. But at this, with this, the flow can be described. Of course, you cannot describe the flow totally now still, because you don't have know the density, and density is of course dependent on temperature, and that is how essentially the combustion couples with turbulence through essentially this density variation at one level. That is, combustion creates heat release increases temperature, temperature reduces density, and density goes into your continuity and your momentum equation. So this is one level of coupling. Of course, you will see that this leads to other level of coupling also, because because combustion is essentially leads to consumption of the species, and that has other sorts of couplings, and through how it couples with temperature. So that we will come in this form, but now at least we have the flow sorted out. Okay. So now we will go into because this is a turbulent combustion course, we will go into essentially looking for the, we will go back to the species and temperature equations, and we will see how we can tackle those, and if those can be tackled in these manners which is similar to the eddy viscosity type of closures. We will see that these are more problematic. There are more complexities that arise when you try to apply this kind of closures for the temperature and the species equation, but we will have to deal with that. Okay. So let us go into the temperature and the species equations. So if we reconsider the energy equation in T form, that is, and with the assumption that your Cpi is equal to Cp, your P is equal to constant, and your Q radiation is equal to 0. So we arrive at a simplified temperature equation, which we devised, which we obtained previously from the enthalpy equation essentially. Left hand side temporal term, convection term, plus diffusion term, thermal diffusivity, plus heat release rate. Okay. And the heat release rate is of course given by number of species, enthalpy of formation, reaction rate, or the production and destruction of that species. And similarly, the species equation is this one. These parts are mainly from, but we do not follow Law's book anymore. We are essentially going into Peters's book and Peters's lecture notes. So you can, if you want to read more about this, you can find this in Peters's book, Turbulent Combustion. Whereas we have assumed that dij is equal to di, okay, and this is of course the corresponding species production and consumption or consumption rate. Okay. Now what we will do is that in the following we will use this term called reactive scalar. Okay. So reactive scalar is nothing but a vector which contains the mass fraction of all the chemical species and temperature. Okay. So reactive scalar, of course, as you see, these are not passive scalars because you have got source terms here in or source or sink terms in these things. So these are not passive scalars, these are reactive scalars, and furthermore this also couples with the flow directly because of the density variation. Okay. So this reactive scalar given by xi I is equal to y1, y2, yn and t. Okay. So there are n plus 1 reactive scalars. So this reactive scalar is essentially the vector. Okay. Now based on these equations we can write one governing equation for a reactive scalar which is given by this form, which is essentially just simplifying these two equations in this form. Okay. Now, for of course, I is equal to 1 to n, di is di, but for n plus 1, di is essentially alpha, w n plus 1, or we write it like this, d n plus 1 is equal to alpha, w n plus 1 is equal to w t, which is the heat release rate, minus 1 by C p times summation I is equal to 1 to n H I is not W I. Okay. Now, so these are our governing equations for the reactive scalar for both the species as well as temperature. So, how can we apply? The question is, can we apply this kind of averaging techniques that we applied for the continuity as well as the momentum equations into these equations of the reactive scalar itself? Okay, and that will be very attractive. Okay, then we can just only solve for the average flow, and of course, if required for the variance flow, variance of these quantities also, and then we have a very good understanding of entire things. So, but it turns out things are not so simple. As such, even in the previous case, when you introduce this concept of eddy viscosity, that has some limitations itself. That does not work too well, because you are essentially mapping one tensor, which is this the Reynolds stress tensor, to the strain rate tensor through one scalar, which is this nu t. So, there are problems. So, that does not work too well. But you will see that even if you can have a reasonably good description of the flow, the problem here are even more fundamental when you try to do the averaging concepts for this. But then we still keep on improving the models, and we will see how the models are done, and we need to have a very good understanding of this how this model works, because this averaging of this averaged form of this continuity, average form of the momentum, and average form of these equations of this reactive scalar equation and temperature equation are very much used in the industry, especially if you are a combustor designer or an engine aero engine designer. And so we really need to know what are the things, and what are the models, what are the problems with that models, what are the problems with averaging, and how we can improve those kind of things. So that is the motivation for this class. Okay. Now, let us go into the this averaging this reactive scalars in different forms, and basically this approach will be called the moment methods for average scalars.